This is Calc 1 and problem session 3. So I'm going to spend an hour doing problems, but I'm happy to start answering questions about either the material on limits or any of the problems about limits that you might have. Any problems that I can do for you? So we are talking about limits and some of their properties. So these are collected in section 2.3 of the text. And let me write some of these properties now. So suppose you have the number c and the functions f and g, and the limit of f of x as x approaches c is L, and the limit of the function g of x as x approaches c is k. So you can think of this as this is the graph of y equals f of x. And here you have the point x equals c. And as you approach c from the right or the left, the value of the function approaches L. That's the idea of a limit. And limits have certain properties. For example, what are called scalar multiples. You multiply a limit by a number. So if you take the function f of x, multiply it by the number b, and take the limit of this as x approaches c. This is just b times the limit of f of x as x approaches c, and this limit is L. So this is b times L. If we take the sum of the two functions, or the difference, if you take the function f of x plus g of x, so it's the sum of these two functions, the limit of this as x approaches c is just the limit of f of x as x approaches c, plus the limit of g of x as x approaches c. So the limit of the sum is the sum of the limits. This is L, this is k, so this is L plus k. And if you took the difference instead of the sum, you would have the difference of the limits. We also have a nice property with respect to taking the product of functions. If you take f of x times g of x, the limit as x approaches c is just the product of the limits. The limit of f of x as x approaches c times the limit of g of x as x approaches c. That's L times k. And we can divide, so long as we're not dividing by 0, the limit of f of x divided by g of x as x approaches c is the limit of f of x divided by the limit of g of x, which is L over k, so long as the denominator isn't 0, right? You can't divide by 0. And we can also take powers. The limit of f of x to the n as n approaches c is just the nth power of the limit of f of x as x approaches c. That's L to the c. So these are 5 basic properties of limits, which we use all the time. And one of the nice instances of this is to evaluate the limit of a polynomial. So for example, if we had the polynomial 4x squared plus 3, and we wanted to take the limit as x goes to 2, by the addition rule, the sum rule, this is the limit of 4x squared as x goes to 2, plus the limit of 3 as x goes to 2. This is a scalar times a function. This is 4 times the limit as x goes to 2 of x squared. And for a constant function, the limit is 3. And this is a power. This is 4 times the limit of x as x approaches 2 squared plus 3. This just says as x goes to 2, x goes to 2. So this is 4 times 2 squared plus 3. 2 squared is 4. 4 times 4 is 16. Plus 3 is 19. So this limit is equal to 19. And that's exactly what you get if you evaluate this polynomial. If you let p of x be 4x squared plus 3, when you evaluate the polynomial at 2, you get 4 times 2 squared plus 3 is 19. And when you have polynomials or rational functions, and you want to calculate a limit, all you really have to do is substitute in for the variable. Right. Any questions about this or any homework problems you would like me to do? So here's an example we saw last week, I believe, or maybe on Monday. Suppose you have the rational function. A rational function is a quotient of polynomials. And this is only defined, this function, let me call it f of x, is not defined when the denominator is 0. So this is only defined for x different from 1. And if we want to take the limit of f of x as x goes to 1, that's the limit of x cubed minus 1 over x minus 1 as x goes to 1. This is not the quotient of the limits. Because this denominator would be 0. So this is not true. You can't just divide. So you have to be a little bit more clever, and you have to remember some high school algebra about factoring. So x cubed minus 1 factors into x minus 1 times x squared plus x plus 1. So this means that x cubed minus 1 divided by x minus 1 is x squared plus x plus 1 for x different from 1. So as x goes to 1, the limit of x cubed minus 1 over x minus 1 is the same, because you never let x equal 1. When x is different from 1, this ratio is x squared plus x plus 1. And this is a polynomial. They just plug in x equal 1. You have 1 squared plus 1, which is 3. So this limit is 3. And this is sometimes called the dividing out technique. So here's another example. Suppose we want to take the limit as x goes to minus 3 of x squared plus x minus 6 over x plus 3. Again, you can't just plug in x equal negative 3 because your denominator is 0. But this factors, the numerator factors, and you can divide out. X squared plus x minus 6 is x plus 3 times x minus 2. How do I know this? Well, It's high school algebra or pre-calculus, but in any case, factoring simple quadratics is something you are expected to know in calculus. So if I divide by x plus 3, the x plus 3's cancel, and this is x minus 2. So this is the same as the limit as x goes to minus 3 of x minus 2. And now you just substitute in minus 3, minus 2, or minus 5. That's the answer. Okay. Any questions about this? Now, there's also a technique called rationalizing.
Professor?
Yes.
Yeah, can you, is it possible for you to focus the camera a little bit more? It's kind of hard to see a little bit.
Let's see. Let me go back to the previous page. Is that any better?
Yeah, I think so, a little bit.
Yeah, so the camera doesn't focus. I mean, this is it, but I can change the light and maybe this makes it a little bit clearer.
Yeah,
So,
that definitely.
yeah, okay. All right, so here's another problem that looks difficult, and it is until you learn the technique. We have the square root of x plus 1 minus 1 divided by x. So if this were a function, what is the domain of definition of this function? First, the denominator can't be 0, so this is defined for x different from 0. But also what's under a square root can't be negative. So x plus 1 has to be greater than or equal to 0. So x is greater than or equal to minus 1. So this function is defined for all x greater than or equal to minus 1 except 0. But we might be curious whether, as x approaches 0, this function has a limit. So the technique here is to use the following, if you like, trick. So you remember there's one basic factorization formula, which is that a squared minus b squared is a minus b times a plus b. So if you let a be equal to the square root of x plus 1 and b equal to 1, what does this formula say? A squared minus b squared. Well, when you square the square root, you get x plus 1. And when you square 1, you get 1. So a squared minus b squared is equal to x. So this says that x is equal to a minus b times a plus b. And the point of this is that you notice that square root of x plus 1, that's exactly my numerator. So if I rearrange this, the square root of x plus 1 minus 1 divided by x, divide by this and divide by this. This is 1 over the square root of x plus 1 plus 1. So another way to write that is the following. The square root of x plus 1 minus 1 over x is the same as square root of x plus 1 minus 1 over x, and then multiply top and bottom by the same thing, square root of x plus 1 plus 1. And this times this is x. This numerator is x. This is x over x times the square root of x plus 1 plus 1. And the x's cancel. So this is 1 over the square root of x plus 1 plus 1. So what I'm taking the limit of as x goes to 0, square root of x plus 1 minus 1 over x is the same as 1 over the square root of x plus 1 plus 1. And as x goes to 0, x plus 1 goes to 1. Square root of 1 is 1. 1 plus 1 is 2. This is 1 over 1 plus 1. Or a half. So this technique, I mean, the name's not important, but this is sometimes called rationalizing an expression. Okay. Let's look at some examples just of these techniques. So let me do some of the homework problems that are in this section. What about number 9? The limit of 2x squared plus 4x plus 1 as x goes to minus 3. Well, this is a polynomial. When you evaluate a polynomial, you just evaluate the polynomial at the point which is the limit, minus 3. So that's 2 times minus 3 squared plus 4 times minus 3 plus 1. Minus 3 squared is 9 times 2 is 18. Minus 12 plus 1 is 7. Number 12, this is not a homework problem, but it's a nice problem. The limit as x goes to 4 of the cube root of x plus 4. So this is just the limit as x goes to 4 of x plus 4 to the power 1/3. So that's the same as the limit of x plus 4 as x goes to 4. And I take the cube root of that. As x goes to 4, x plus 4 goes to 8. So this is 8 to the 1/3. And the cube root of 8 is 2. What about the limit as x goes to pi over 2 of sine x? Well, sine of x is a nice function. As you approach pi over 2, sine of x approaches 1. This is the sine of pi over 2, or 1. What about the limit as x goes to pi of the tangent of x? So of course, the tangent of x is sine x over cosine x. And we can use the quotient theorem for limits. The limit of sine x as x goes to pi is 0. The limit of cosine x as x goes to pi is -1. 0 over -1 is 0. What about number 45? That's the limit as x goes to -1, x squared -1 over x plus 1. Now, we can't just plug in -1 for x, because the denominator would be -1 plus 1 is 0. But we use division or factoring. We know x squared -1 is x plus 1 times x minus 1. So x squared -1 over x plus 1 is x minus 1 for x not equal to -1. So this expression, this is the same as x minus 1. And as x goes to -1, x minus 1 goes to -2. Any questions about this? I mean, pre-calculus and high school algebra are prerequisites for calculus, and you really do need to know them. You have to be able to do this kind of factoring. Let's do a few more problems. This is number 46. This is the limit as x goes to -1. I have x plus 1 in the denominator, which means I can't just plug in -1 because this would give me 0. And the numerator is 2x squared minus x minus 3. So my only technique for solving a problem like this is to hope that I can factor the numerator and divide out by x plus 1. So it would be good if 2x squared minus x minus 3 was equal to x plus 1 times something. And if you check or figure it out, x plus 1 times 2x minus 3. If you multiply that out, you get 2x squared. 2x minus 3x is minus x and minus 3. Perfect. So this is the limit as x goes to -1 of x plus 1 times 2x minus 3 over x plus 1. And the x plus 1's cancel. So this is just the limit of 2x minus 3 as x goes to -1. And this approaches -2 minus 3, or -5. Any questions about this? Let's look at a few more that are interesting. This is number 50. Suppose we have the limit of e to the 2x minus 1 over e to the x minus 1 as x approaches 0. Now, the limit as x goes to 0 of e to the x minus 1 is e to the 0 minus 1, which is 1 minus 1 or 0, which means if I just plug in x equals 0, I get a 0 in the denominator, and I can't do that. So I have to hope I can factor this. And I can, because e to the 2x minus 1, e to the 2x means e to the x squared minus 1. So by our basic factorization formula, here's an instance, a squared minus 1 is a minus 1 times a plus 1. And I let a equal e to the x. So this is e to the x minus 1 times e to the x plus 1. So e to the 2x minus 1 over e to the x minus 1 is e to the x plus 1. So this is just the limit as x goes to 0 of e to the x plus 1. And as x goes to 0, e to the 0 is 1. 1 plus 1 is 2. So this limit is 2. So let's pause for a minute just so you can look at some of these problems and other problems perhaps. And if you have any questions about them, this is the time to ask. And if there are any other questions you would like me to do, then this is the time to ask me to do them. Okay, well, let's do another couple of problems because it's a lot of fun. Let's do some that involve rationalizing. So number 57. This is the limit as x goes to 4 of the square root of x plus 5 minus 3 over x minus 4. And again, you can't plug in x equal 4 because the denominator would be 0, which is not good. But I can take this and multiply by the square root of x plus 5 plus 3 over the square root of x plus 5 plus 3. Because this, anything over itself, it's just 1. This is, I'm just multiplying by 1. But now I see that this is of the form a minus b times a plus b. So what do I have in the numerator? I have this times this, that's x plus 5, minus 3 squared over x minus 4 times the square root of x plus 5 plus 3. This is the limit as x goes to 4. X plus 5 minus 9, 5 minus 9 is 4, minus 4. X minus 4 over x minus 4 times the square root of x plus 5 plus 3. And these terms cancel. So this is the limit as x goes to 4 of 1 over square root of x plus 5 plus 3. And now when x goes to 4, we don't get a 0 in the denominator. We get 1 over the square root of 4 plus 5 plus 3, which is the square root of 9 plus 3, which is 3 plus 3, which is a 6th. So this looks like a very complicated problem, and it is a bit complicated, but we can still do it. And the answer is a 6th. Remember, we proved some trigonometric limits that the limit as x goes to 0 of sine x over x is 1. And the limit as x goes to 0 of 1 minus cosine x over x is 0. So if we look at a problem like number 69, the limit as x goes to 0, sine x over 1 minus cosine x over x squared is x times x. I can think of this as the limit of sine x over x times 1 minus cosine x over x. And the limit of the product is the product of the limits. This limit is 1, this limit is 0. So we get 1 times 0, or 0. Let me explain how I got these two limits. So they're basic trig limits that we use a lot in calculus. And it uses something called the squeeze theorem. There's a very pretty picture in the book says the following. Suppose we have a function f of x, which is squeezed between two functions, g of x and h of x. So let's say this is the function y equals g of x, and this is the function y equals h of x, and squeezed in between them is the function y equals f of x. Right? This red curve, the graph of f of x, is squeezed between g of x on top and h of x on the bottom. And let's say at some point L, the limit of g of x as x goes to, at some point C, the limit of g of x as x goes to C is L. And the limit of h of x as x goes to C is also L. So if you look at this function on top, as you approach x equals C, that's this point, the function is approaching L. And below, as you approach x equals C, the function h of x is approaching L. And this function f, which is squeezed between them, has to have a limit, the same limit L as x goes to C. That's the squeeze theorem. Let's look at an example of that. Suppose I take an angle theta, and this is the unit circle. So this is the point 1, 0. This is the point 0, 1. This is theta. What are the coordinates of this point? Well, the x over this is cosine theta. And this over this is 1, is sine theta. So if you have an angle theta coming out of the origin, it hits the circumference of the unit circle at the point whose coordinates are cosine theta, sine theta. Let me draw a bigger picture of that. So here's the angle theta. This radius is 1. The coordinates of this point are cosine theta, sine theta. What are the coordinates of this point? Well, the x coordinate is 1, and the y coordinate, well, this over 1 is the tangent. So this point has coordinate 1 and tangent theta. So I want to look at 3 different regions. First of all, I have this blue triangle. This is 1, this is tangent theta. So for the blue triangle, the area is a half the base times the height, a half tangent theta. I also have this green triangle. The green triangle, the base is still from 0 to 1. This point is cosine theta sine theta. So the height is sine theta. So the area of this green triangle is a half the base 1 times the height. And of course, I have also the sector of the circle. And the area of a sector of a circle cut out by an angle theta radians is theta over 2. Theta over 2 pi, the area is pi. And what we have is the green triangle is contained in the red sector, is contained in the blue triangle. So the area of the green is a half sine theta. That's less than the area of the sector, which is theta over 2, which is less than the area of the blue triangle, which is a half tangent theta. If we multiply by 2 just to get rid of these 2's, I have sine theta less than or equal to theta less than or equal to tangent, and the tangent is the sine over the cosine. So if I rearrange this, sine theta over theta is less than 1. And from this, sine theta over theta is greater than or equal to cosine theta. So what does my picture look like? Here, I have the function g of x equal to 1. Cosine theta, let's say from minus pi over 2 to plus pi over 2, looks like that. And sine theta over theta is squeezed in between these two. So by the squeeze theorem, so I have the limit of g of x as x goes to 0, and the limit of h of x goes to 0. These are both 1. So that means the limit of sine theta over theta as, or sine, well, I should call this theta. Sine theta over theta is squeezed between this, so it also has to equal 1. Anyway, there's a whole lecture on this on YouTube, and it really is worth spending a lot of time trying to understand the concept of a limit and how to solve these problems. So I'm going to have Zoom office hours. They're completely optional. They're just a time when I'm online. You can come online and ask some questions. I'll have one tomorrow evening, 6:30 or 7 o'clock, and one probably on Friday morning, because next week we have no class. Right? We meet on Monday and Wednesday, and Monday and Wednesday are both holidays. CUNY is closed. So our next formal problem session will be 11 o'clock a week from Monday. But I will have some office hours when I'm available. Are there any questions or any problems you'd like me to do? If not, then I guess we will quit for the day.
Professor?
This limit I just did, though, is very important. It's really worth spending some time to try and understand this proof. Yeah, was there a question?
Yeah, so today's my first day here. So I looked at the syllabus and I'm looking at like the homework and stuff, but I don't really know what that refers to. Like, is that just the lesson homework for that?
So here's the syllabus. So for example, today I was discussing lesson 3, evaluating limits in the squeeze theorem. And the homework, and there's also lesson 4. So we'll talk about this more in a week and a half. So the problems associated with lesson 3 and 4 are in the textbook, section 2.3, 9 to 21 odd, 37, 43, and so forth. So these are the homework problems. And the due dates are on Blackboard. So you do the homeworks, you convert your pages into a PDF file, and you upload the PDF file to the appropriate section in the assignments part of the Blackboard website for this course. It'll say assignment 1, assignment 2, and so forth. And the only way I have to look at your work and grade it is by going through Blackboard. So, and that's also the way you'll take the exams, exactly the same thing. You'll write out the solutions, make a PDF file of your pages and upload it to Blackboard.
Okay, so one second. So all these numbers 1 through 14, 19, all those numbers are what we'd be doing for the homework, essentially?
So, right, so the homework problems for every lesson in the course are on the course calendar on this sheet.
Okay.
So for the whole semester what the homework assignments are.
Okay. My last question is, do you necessarily have to scan it, or can I just take a picture on my phone and send it that way?
That's not right. You can do that. I prefer a PDF file because then it's one file. If you have to take pictures, then you might end up with 10 separate pictures and it's more complicated to upload. It's more complicated for you because you have to upload 10 pictures separately, and it's more complicated for me to read. But most printers scan and convert to PDF files. But if you don't have access to a printer and you have to use your cell phone to take pictures, then that's what you do.
All right. Thank you.
Sure. Other questions? Anything else? Okay. Then we are done for the day. Again, I'll have office hours Thursday and Friday, and the next official class session is in a week and a half. It's on Monday, September 13th. Okay. Bye all.